Try this. Okay, so so the question is, I'll ask again now that we're recording, how big should your sample sizes generally be? There's actually two rules, and it depends on the, so the short answer is it depends. Okay, it depends on what?
How big your population is.
Does not depend on how big your population is.
I don't know.
No, no ideas? Okay, so if you have discrete data, your NPQ must be greater than or equal to 10. Okay, if you have continuous data, the answer is it depends. Typically, with continuous data, we want our n to be greater than or equal to 30. Or we can do what we're going to introduce today, which is called a QQ plot. Okay? Sometimes you can get away with smaller sample sizes if you do a QQ plot. So, so that's a good introduction into section 7.3. 7.3, which is assessing normality. Okay, so we're going to talk about how to draw a QQ plot. Is also called a normal probability plot. Okay. All right, so I don't know why in the world they do not put this formula on the formula sheet. I will try really hard to remember it, but I would ask you guys, I don't make you memorize any formulas. This is the one I'm going to ask you to memorize because I gave you all the others. And sometimes I forget to put it on there. But the formula is f sub I. Well, I'll give that to you in a second. Well, actually, I'm going to show you the steps. So number one, your steps are to arrange data in ascending order. Number two, this is the formula I want you to remember. Compute f sub I equals I minus 0.375 over n plus 0.25. Okay, that's the formula that for whatever reason they left it off your formula sheet. I'm going to ask you to memorize it. I will try to get it to you, but sometimes I forget. Okay? So I equals your index. Somebody asked me to repeat something. Or not. Okay? Step number 3 is compute the z-score. And number 4 is plot the observed on the horizontal and the expected z-scores on the vertical. Okay, so let's do an example here. If you'll open up Canvas, go to worksheets, in-class worksheets at the bottom.
Is the EXP accept?
Expected. And oh, it's worksheet 7.4, although this is, they changed my order. Yeah, I should rename that, but anyway. It's called 7.4, but this is actually 7.3. Okay? All right. So let me share this document so you guys can see it on the video. Share. Okay. The following is the finish time in seconds of 6 random races for a greyhound dog named Barbie's Bomber in the 5/16 mile race. Why did they come up with 5/16? But whatever. They're gamblers. What was gamble on dog races. Or you gamble on dog races, you got a problem with gambling. Is there a reason to believe these are normally distributed? Now, Eric did say, when I asked, I don't remember if that was on video, so I'll repeat it. How big should your sample size be? It should be as large as possible. However, you don't want to kill your dog. So you only get 6 raises because the dog's probably going to be out of breath. Okay? So sometimes you can't get, well, it would be nice to have as large as possible. 6 is very small. It's obviously much less than 30. So the question is, we don't want to kill our dog. Does this data look normally distributed? Oh, and I forgot to mention here, I'll put this as 4A, your hope for a straight line. Okay, so that's an important piece here. All right, so who remembers how to sort the data? Tanner, I'm going to pick on you. Select data. Off to the right over here, sort and filter. And we're going to sort smallest to largest. Okay, ascending order. Okay, so that was pretty easy. Now, it says compute f sub I, where I is your index number. So what I'm going to do is I'm going to create a column here called index number. This is basically 1, 2, 3, 4, 5, 6. It's just number them sequentially. In this case, 1 through 6. Okay. Now we're going to compute our f sub I. F sub I. Okay. All right. So according to this formula here, my numerator is going to be I, which is the index number that I just put here, and I'm going to subtract 0.375. I'm going to divide it by the denominator. What's my n in this case?
N is 6.
N is 6, so I'm going to divide everything by 6.25. Okay? All right, do I need to F4 any of those? No. Okay, so I'm going to copy these down. So this F sub I represents the, you can think of those as your percentiles. Okay? All right. Now,
What is the N?
the N is your sample size. Okay, I'll put that in. N equals your sample size. Okay. All right, so do you guys remember how to find the z-score using Excel? You need to know that for the test. For those of you who haven't taken the test yet, you need to know this for the test. Norm S inverse. Now, there's 2 of them here. The one without periods is, actually, it doesn't matter whether you use periods or not periods, but I think the one without periods is the one I prefer. Actually, I should put this as z-score. So it equals norm S dist, norm S inverse, excuse me. Norm S inverse, and then you can think of these all as the probability. If you get if f sub I greater than 1, you got a problem. Or if you get a negative value, you got a problem, okay? You can think of those as probabilities, okay? So if this data were normally distributed, those would be your z-scores, okay? All right, so now, so we've computed our z-scores, we've done set 3. Now we're gonna plot the observed and the expected. So this is gonna be your observed. I'm gonna hold the control key down. I'm gonna highlight my z-scores. I'm gonna say insert, scatter plot, 2D. So what do you think? Does that look like a straight line to you? Yeah, decently straight, okay? Now, one of the unfortunate things, oh, actually, I'll throw this out here. Oh, I should have looked at that before class. I didn't think about it. In your book, go ahead and if you want to open up your book. With 7.3, here we go. So, in fact, you can see on page 383, maybe I will hold this up to the camera so that those at home can see this. I'm going to stop sharing. So you can see here, there's the plot we just did. It works really well. Now, in the book, they've got these really cool plots that have these, whoops, right here. I can't see what I'm doing. They've got these boundary lines. Do you see that? Okay. Now, what's really nice is when you have those boundary lines, it makes it really easy. If it's within the boundaries, then you say it's normally distributed. And if it's not, then it's not normally distributed. So, for example, here, let me show you this other example here. You can see this one has a big curve. Do you see that? Okay. So that would not be normally distributed. Now, the other thing that I just want to mention back here, at the beginning of class, I said, if your n is greater than 30, it's often normally distributed, but I want to emphasize this is not a magic number. And in fact, if you look at this one on page, or maybe we will, I might have this on here, I can't remember. Figure 35 on page 385 here. One of the things you can notice here, your data is a lot more than 30. It's not normally distributed. So the fact of the matter is, whenever you're doing some sort of an experiment like this, normally if your n is greater than 30, you're probably going to do some sort of a histogram. You wouldn't do a QQ plot because you can do a histogram. So the histogram is typically for small sample sizes. So, you know, sometimes you'd love to have a large sample size, but sometimes, you know, you can't get one. So, for example, let me just say this. One of my online classes, we actually had students watch this like 2-hour documentary. It was called Super Croc. Okay, very interesting documentary. So basically, what it was is they found in the desert in Africa a crocodile head, the head only. They didn't find the rest of the crocodile, only the head. The head was 6 feet long. It was as big as me, just the head. So this was a prehistoric a dinosaur, basically, a crocodile. So what that told them was a couple of things. Number one, crocodiles only live in swamps. And so this desert at one time was a swamp in Africa. Number two, they wanted to figure out how long was this crocodile. Okay? They had a sample size of 1. You can't just invent crocodile heads there, you know. So what they decided to do is they wanted to do some sort of a regression. And so they took modern crocodiles from a caiman, which is kind of a small crocodile, to alligators to crocodiles. And they measured their proportion of their head size to their body size, okay? Now, like I said, it would be nice to get a sample size of 30 as a minimum, although that's still not a magic number. In this case, they had a sample size of 1. You can't even do a normal probability plot with that. Okay, it's what you got. Okay, you deal with what you got. But just curious, how long do you think this crocodile was if the head was 6 feet long? It was 40 feet long. Like they did a model of it. It took up a whole room. Like it's just huge. So I'm so glad they don't have 40-foot long crocodiles now.
Glad I lived in Utah. I didn't know that.
Yeah, well, there probably were back in prehistoric times. Utah's actually a really good hotbed for dinosaurs. So anyway, so the homework and the quiz tomorrow is basically going to be looking at QQ plots, but I will say this, I'm not going to give you a quiz on how to create this, but it will be on the test, how to create these. So you got a nice video here to do that, but definitely this will be a test question, okay? So any questions that you guys have on that? All right, well, So that's 7.3. Let's move on to 7.4, which is very different. 7.4, which is a normal approximation of binomial. Okay. So what we're going to do, now let's think about the binomial. What kind of a distribution is the binomial distribution? Is it discrete or continuous? Okay, the binomial is discrete. Discrete meaning whole numbers, right? Whole numbers. What is the normal? Discrete or continuous? Yeah, it's continuous. Okay? So let's just remember, can I say the probability that x equals, say, 3? Is that a legitimate thing to do with a discrete distribution? Yes. Remember, because it's discrete, if you have something that you're going to have something that looks like this, maybe. Okay. So this is 0, 1, 2, 3. So I could find the area of this. That would be the probability, right? Okay. On a continuous, can I say, so this will equal some decimal number. So on a continuous, what's the probability that x equals 3? It's going to be 0. Okay? Because the problem is, if I superimpose a normal curve onto this, let's say it's normally distributed, the value 3 has no width, right? So under the normal distribution, probably that x equals 3 or any other number is going to be 0. Okay, so the idea here is, if your n is large enough, if n is large enough, you can use the normal distribution to approximate the binomial. Okay, how large is large enough? I just told you guys, there's bigger than 10, right? So this rule here. So your NPQ must be greater than or equal to 10. Okay? Now, you guys are so young, it kills me here. Have you ever heard of a fudge factor? What's a fudge factor? Sure.
It's the possibility of there being error in calculation. It's about plus or minus 3%, from what I've heard.
Oh no, that's not what I was thinking of.
Kind of what you always say, there's a fudge factor if there's any possibility that there's something wrong.
You're gonna fudge the numbers, that's what that is. Okay? Sometimes you call that a fudge factor. You just add a number to it if you want to. So the idea here is, let's look at this. So let's go back here for a minute. Now we know that with the continuous distribution, the probability that x equals 3 is going to be 0. Okay? So what I'm going to do is I'm going to fudge the numbers a little bit because I've got to give that some space. Okay? So under the normal approximation, rather than doing the probability that x equals 3, what I'm going to do is I'm going to say x is between 2.5 and 3.5. Okay? Now notice I put some equals there. Does it matter if I put the equals on there?
Yes.
No, it doesn't. Why? Why does it not matter? What's the probability that x equals 2.5 under the normal distribution? It's 0. What's the probability that x equals 3.5 under the normal distribution? 0. Okay? So we refer to this is what I affectionately call my fudge factor.
So why you put this equal C sign? Why you put
Because I got to have it too, and it doesn't matter. It doesn't matter. With the normal distribution, it doesn't matter. With the discrete distribution, it does. But the discrete distribution can never be 2.5. So it doesn't matter. Okay? All right, so because the idea here is, if I'm going to do a normal distribution, I've got to give it a little bit of a gap here. Okay? So let me give you, the idea here is, let me give you a nice little table. I'm going to set this over here. Okay, so when we're doing the normal approximation of the binomial, the idea here is the exact, and I'm going to put binomial distribution, the probability that x equals some value a, okay? Well, I can't let it equal the a under the normal approximation, normal approx. And so what I'm going to do is I'm going to say, well, x is between a, let me give myself a number. X is between a minus 0.5 and a plus 0.5, okay? Because once again, going back to my picture here, I've got to give it some space, okay? I'm going to add and subtract a half to whatever my value, if this is 3 or 2 or whatever it is, I'm going to add and subtract a half. Now, why am I doing that? Because I'm trying to use a continuous distribution to approximate a discrete distribution. Okay? So I only do it in this case. Now here's what's going to happen. Is in the future, I'm going to ask you to find the probability of some continuous distribution. And you guys are going to add and subtract a half because you remember this lesson. But the question is, you only do that because you're using a continuous distribution to match a discrete distribution. So only do it when you're supposed to, is what I'm trying to say. Don't do it when you're not supposed to.
Okay. Can you tell us what we're supposed to?
No, I'm not going to tell you. You got to remember this. Okay?
What would be an example where you'd be comparing continuous and discrete?
This is the only example that you're going to compare the continuous with the discrete. So this is the only case.
Like, how would you word it in a question? That's my question.
So I would say find the probability that x equals some value. And then you have to understand, am I talking about a discrete distribution or am I talking about a continuous distribution? And I'm not going to make that super obvious in the question. You have to understand the context of the question. Is it a binomial? Is it not a binomial?
So are we going to be able to tell because it is a less, greater than 10, the NP?
Yeah, so people are going to mix up this rule. Is it 10 or 30? People mix up that rule all the time too. So what I'm trying to say is you have to be super observant. I'm not going to give you any special clues in here. You've got to figure that, is it a discrete distribution? Is it a continuous distribution? Now, the main discrete distribution we have is a binomial. Is it a yes, no, true, false, something like that? So from that information, you'll say, yes, it's a binomial. No, it's not a binomial.
I guess my question is, like, if you were to say, what's probably the probability that x equals 3, and we know it's continuous, like we find that out. But how do we know if we just say it's 0 or if we have to do this minus 0.5 plus 0.5?
And that's what I'm trying to say. You got to understand the context of a problem. I can't give you a rule here, and I know it's going to be confusing. On the homework, you're always going to be doing this, so it's going to be easy on the homework. As we learn the rest of this week and next week, it's going to get confusing for you. Okay?
Could you make is there any homework questions in this book that?
Yeah, they're going to be in chapter 7 and 8 and probably 9.
Oh.
And 10 and 11 and 12 and 13 and 14. Okay, so let me finish out this table. Okay, so if it's so really what we're saying is you've got a binomial distribution and we're doing a normal approximation. Now you're probably going to be asking me, why would I do such a thing? And I'll answer that question in just a minute. If I have the probability that x is less than or equal to some value a. Okay, now this is a discrete distribution here, right? We're going to what we're going to do in this case is we're going to say we want x, probably that x is less than or equal to a plus 0.5. So for example, let me go back to here. So I've got the probability that x is less than or equal to 3. Okay. Now, if I stop at 3, I'm going to miss all of this area here. Okay. The idea with the normal approximation, you're trying to make this as large as possible. So you don't want to stop at 3. You're going to add a half to this, and you're going to make this 3.5. Okay. Does that make sense? If you're doing the probability that x is greater than or equal to some value a, then what we're going to do is we're going to say probability that x is greater than or equal to a minus 0.5. So going back to here, pick another color. If I want the probability that x is greater than or equal to 3, okay, so I want all of this area here, but I don't want to stop here. I want to include this area as well. So that's why I'm going to say, in this case, probability that x is greater than or equal to 2.5. Because I want this area to be as large as possible. Okay? So when you're looking at these, sometimes this seems a little bit backwards. But that's why, this is why, I know some of you really hate to draw graphs. Okay? This is why I asked you the question, WWRD, what would Rick do? Rick would draw a graph so he doesn't have to remember this stupid table. Okay? Make it as big as possible. If I want to be greater than or equal to 3, I'm going to go to 2.5. Okay? Because I don't want to miss out on this piece here. If I stop at 3, I'm going to miss out on that piece, and I'm going to underestimate it. Okay? Now, finally, if I want the probability that x is between a and b, okay? So let's say the probability that x is between 2 and 4, okay? If it's between 2 and 4, as I pull out another color here, I want 2, I want the 3, and I want the 4 in this case. Okay, so in this case, I want the probability that x is between, I'm going to go from a minus a half to b plus a half. So I'm going to be doing both because I want it to go, because I don't want to stop here and here. That's 2 to 4, right? I'll miss all of this piece and I'll miss all of that piece if I just go from 2 to 4. So I want to include a minus a half, so 1.5 to 4.5. Does that make sense? Okay, now I know a lot of you are probably saying, why would I even want to do this? Which one's more accurate, if I did the binomial or if I did the normal approximation? Which one's more accurate? The binomial, because yeah, you're doing the area of these, and you can see here on my curve. See it. This is going to be a little. I'm kind of shorten that a little bit, but I'm kind of making it up for because this is a little bit shorter here. Okay. Now, let me give you an example of why I would want to do this, and let's remember that we didn't used to have computers back in the 50s. In the 40s, okay? So let's say, for example, I'm going to go over here to Excel. Oh, I didn't, oh, I should have done that. Here, I'm just going to open up a new page. If we have time at the end of class, we'll do another normal probability plot, because that's an interesting one there. All right. Let's say, for example, the Red Cross says 7% of people have O negative blood. Take a sample of 500 people and count the number of O negative blood. What is the probability that fewer than 30 have O negative blood? Okay, All right, so the first question that I want to ask you guys, we're going to go back to this question here. Because it didn't state it specifically in the problem. This is why you guys have to figure this out. Is this a discrete or is it a continuous distribution?
Discrete.
Discrete because?
People can have 45 people have a negative blood. It has to be whole numbers.
Okay, it has to be whole numbers. And so the question is, so if it's discrete, our favorite distribution for discrete, because we don't learn Poisson in this class, is binomial. There are other discrete distributions besides binomial. We're just not going to learn about them. Okay. Now, before I gave it to you as a binomial, why is this a binomial distribution? Either you have O negative blood or you don't. Okay. We repeat it a fixed number of times. What are the fixed number of times we're repeating this? 500 times. And what was the fourth? Oh, these are all, we're assuming these are all independent. Okay. Now, back in the old days, when we didn't have computers, we're going to compute the probability of fewer than 30. So let's think about that for a minute. I want the probability that x is less than or equal to 30. No, it says fewer than 30. It says less than 30, right? Now, it's a distribution, so the equals matter. It's a discrete distribution, so the equals matters, right? So less than or 30 is the probability that x is less than or equal to 29. Okay, because this is discrete. Okay, it's discrete, so 30 has areas. The idea here is I've got some sort of binomial distribution here, whatever, and it's going to have a lot more bars than I just drew on the board. Okay, so the idea here is, okay, if I want fewer than say 30, okay, well, that's 29 or less, right? So I want all this area here. Obviously, I should have 30 bars there, but I only do 7. Okay, so here's the deal. Now, even though we're using Excel, we're going to pretend that we have to calculate this by hand. Okay, how would you find the probability that x is less than or equal to 29 by hand? Even with the computer, we'll use the computer, so it'll be a little easier, but it's still going to be a pain in the butt. No, we don't want to find the mean yet.
We don't find the area.
So we have to find the probability that x equals 0, right? We're going to find the probability that x equals 1. And we're going to find the probability that x equals 2, etc., all the way down to probability that x equals 29, right? How do I find the probability of all those? How many calculations do I have to do? I have to do 30 calculations. Okay? All right, so let's do, so my sample space in this case is x. Okay, so I've got 0, 1, 2, etc. I'm going to go down to 29. Okay, now I'm taking away your binom dist command. How would you do this by hand? How would you find out, for example, the probability that x equals 0 or 1 or 2 or whatever you want it to be? Yes. So we're going to use our binomial formula, right? Probability of x equals the combination of n choose x, p to the x, q to the n minus x, right? Okay, so I'm going to make some columns here. I need my combinations. I need my p to the x. I need my q to the n minus x. Okay? Now, I'm using a computer. Can you imagine doing this by hand? Okay? What's the formula for the combinations? column bin. Number is 500. Number chosen, 0. I'm going to click on the 0, right? Okay. Only one. This will get bigger. Yeah. Remember, we don't want to do this sample space. In fact, just for fun, I'm going to copy that down. Look, we're already in 10 to the 13th here by the time we get up to 6. Extra credit right out the sample space before class tomorrow. Okay. All right, p to the x. So what's my p in this case? 0.07 to the, click on the 0. Okay. What's my q? 0.93 to the, and make sure you use parentheses here. What's your n? No, n is 500 minus 0. Okay. And then my probability is going to be over here. This is my probability column. Basically, I'm just going to multiply these 3 numbers together. Now, the probability that x equals 0 is minuscule. 1 times 10 to the minus 16 is tiny. But I'm going to do this for all of those. And now I'm going to figure the sum of this column here to find out the probability that fewer than 30 is the sum of, oops, this column here, which works out to be 0.167. Okay? Now, I should throw this on the test. I make you do it without the binomial distribution command, just to be mean. Okay? Because there's only 30, well, and really more than 30 because you got to figure out the p to the x and the q to the n minus x. Anyway, it's ridiculous, right? There's got to be an easier way, right? And I don't mean binomial dist. Okay? Back in the old days, they didn't have Excel. They couldn't use binomial dist. Okay? So the question is the normal approximation. Okay? Now, if we were doing this here, okay, pretend that this is now a 30, okay, and I want to figure out the area of this blue normal curve, right? If I'm doing it from fewer than 30, this is where this comes in handy. Probability that x is less than or equal to 29. Do I need to add a half or do I need to subtract a half? I'm going to add a half to the 29. Because it said fewer than 30, so you always want to make it an equals in here. And then you're going to add a half, according to my table here. So we're using this one here. Okay? It's going to be fun. Okay, so the idea here is I want the probability that x is less than or equal to 29.5. Okay? Now, with the normal curve, rather than doing 30, I could do this with one calculation. Isn't that much easier to do? Okay? So the idea here is, how can I find the area, if this is 30, how can I find this area to the left? Here. The z-score. So what's my formula for the z-score?
X minus mu.
X minus mu over sigma, right? Now with this, I need to figure out what's my mu, what's my sigma. And I'm going to pick on David because he actually gave me this at the beginning of this. You remember the formula for the mean, for the binomial? You did.
Earlier. Sorry, I'm caught up with the chart.
Yeah. Did you hear what Victor said? What did he say?
NP.
NP. Mean is NP. What's the standard deviation now that you got the hint? Okay, Victor.
NP, well, the square root.
Square root.
NP.
NPQ. Okay. This This is going to be way easier to do, right? Okay, so the idea here is, so I'm going to use the z distribution to do this now. So z equals x minus mu over sigma. I'm going to underline that so it looks like a fraction, but in order to do this, I need to find my mu, which equals NP. I need to find my standard deviation, which is the square root of NPQ. So in this case, what's my N? 500. What's my P? I'm going to multiply those together. So, whoops, times 0.07. That gives me, so out of 500 people, I would expect about 35. Okay? My standard deviation, the square root of N, which is 500, times P, which is 0.07, times Q, which is 0.93. 5.705, okay? So here we go, Z equals, what's my X? What? 29.5, remember? Because I'm adding a half to the 29. Okay, notice all of these have an equals in them, because on the binomial, it's going to be easier to figure out if you have an equals in them. Okay, it's 29.5 minus what? 35. And we're going to divide that by here, 5.7. So this is going to give me a z-score of negative 0.96. Okay, so what I've done here, I'm going to stop sharing for a moment so you can see my board here. So I've got z equals 29.5 minus 35 over the 5.7, whatever the numbers are, which equals negative 0.96. Okay, so what I've done is I've converted this to a standard normal. What's the mean of the standard normal? 0. And I'm almost one standard deviation away. I'm negative 0.96 standard deviations away, right? So I want the area, because it's less than or equal to 29.5. Okay. I need to find this area. How do I do that with the computer? Okay. So that's your z-score. And then say it louder, Jacob.
Norm S dist.
Norm S dist, right? So that's going to be equals norm S dist. Do I need to subtract this from 1? No, because I'm getting the left side, okay, of that. Now, the correct answer is 0.1677. I got a value of 0.1675. Wasn't that way easier to calculate than those first 30 calculations that I did? Okay, do you see why this is very useful? Okay, which one's more accurate? The binomial is more accurate, but this is pretty doggone close, and it was a whole lot easier to calculate than the binomial, especially if I were doing this on a piece of pencil and paper, right? Okay, you would not want to do this with pencil and paper with binomial. Okay? All right. Quiz tomorrow will be on 7.3 and 7.4. It'll be a paper quiz, okay? So I won't make you do n equals 500, x is less than 30. So you need to know the normal, so it's the normal approximation of the binomial and the QQ plots. So see y'all tomorrow.